Right, okay. So we'll start off with the assessment criteria so you know what we're trying to achieve. A minor technical hiccup right at the beginning there, but hopefully you can carry on. So the assessment criteria, as you're probably aware, is set up as P1, which is going to address task 1. That's describe the operation of thermodynamic systems and their properties. Then we'll look at P2, which is explain the application of the first law of thermodynamics, and that's a relatively straightforward law, and you're probably familiar with that anyway. And that's addressed in task 2. And then we've got the P3, the pass criteria, which explain the relationship between some constants for a perfect gas. And we're going to look at things like the characteristic gas constants and the value of gamma and specific heat, constant pressure and specific heat of constant volume. So that's going to be addressing task 3. And then we'll move on to the merit level question, which is calculate the index of a compression in a polytropic process. So we'll look at gas processes, and that'll help you address task number 4. And finally, D1, which is distinction requirements, is what we're going to illustrate the importance of expression for work done in a thermodynamic process by applying the first principle. So we're going to look at a pressure volume diagram and establish how we can determine the work done during those processes. So that's addressed in task number 5. Right, so what we're going to do, we're going to look, first of all, thermodynamic system, what a thermodynamic system is. We'll then look at thermodynamic properties and the system state. We're going to refer to that quite a lot in thermodynamics, the state, the equation of state. We'll then look at the laws of a perfect gas. And then we'll look at the equation of state of a perfect gas. So going on from the properties, developing the state of a perfect gas, the equation of state. And then we'll look at gas processes, and that'll help you with task 5, 4 and 5. Okay, so first task is, so with the aid of sketches, with a sketch in each case, describe the operation and the properties of A, a closed system, and B, an open system. So first of all, let's define a thermodynamic system. So a thermodynamic system is anything that you want to analyze in terms of energy transfer. So anything in space that can be isolated from the surroundings, I'm going to isolate it by means of an imaginary boundary line. So we'll take the process, whatever we want to analyze it, and we'll draw a boundary line around that process just to define what the system is. And what that allows us to do is we're going to be able to look at energy transfer. So if we've got our thermodynamic system, that could be anything at all that you want to analyze. It's not anything particular. So it just could be a cup of tea. And we're going to look, if we draw a boundary around that cup of tea, then we can look at energy transfer across that system boundary. But as you know, if it's a cup of tea standing, all the energy is going to be across the system out into the surroundings, because the temperature of the tea initially will be hotter than the surrounding. So the energy transfer in the form of heat will be across the system boundary from the system into the surroundings. So let's look at a closed system, the definition of a closed system and an open system. So first of all, we have our system. So we have a system boundary. So this is our system that we're going to analyze, whatever we're looking at. Could be an internal combustion engine, anything at all that you want to analyze in terms of energy transfer. Outside, we have the surroundings. Now, it's a closed system, so the only thing that can go across our boundary is thermal energy or heat energy, and we could give that the symbol Q. And the other energy form that can cross the boundary is work energy, and we'll give that the symbol capital W. There's a direction, there's a sign convention that you have to be familiar with. So try and remember this. So the sign convention for transfer of energy from the system to the surroundings. So if it's thermal energy or heat transfer, then out of the system, it's always referred to as negative. and into the system, thermal energy is going to be positive. Now, for now, we're going to look at work transferred across the boundary. So it'd be a piston moving, for instance, and the system expands and the piston drives something. So then the only energy transferred across that boundary in a closed system is going to be out of the system. The sign convention is positive, and into the system, it's going to be negative. Now, the way to remember these sign conventions is that if you have an internal combustion engine here, then the work out of the system is probably useful to you. So think of that as being positive work. So just to recap on that, the sign convention, we have thermal energy out of the system is negative, into the system is positive. And for work energy transfer, the sign convention is the opposite way around. So out is positive and in is negative. It's easier to remember the sign convention for work because positive work out is useful to us. We think of that as positive, and thermal energy is the opposite way around. Now inside the system, it has what we call internal energy due to its temperature. So if we transfer thermal energy out of that system, we're going to reduce its temperature, so the thermal energy within the system is going to change. I just want you to bear that in mind. We're not going to do anything with it at the moment. So just bear in mind this term, the internal energy. We're going to use that again a bit later on. So now we'll look at an open thermodynamic system. It's very similar, except we have something called mass flow that can cross the system boundary. So we have our system boundary, we have our surroundings and the system. It has an internal energy still. Again, we can have heat going across that system boundary, thermal energy, and we can have work energy going across the system boundary. But this time we have, in an open system, we have a mass flow that can cross the system boundary. And we can have mass flow can go in either direction. So we've got to be aware that we can have mass flow going across the system boundary. Now, typically in most systems, that mass flow will remain the same for the in and the outlet. So for a steady flow energy system, and we're not going to look at any other type of system, then the mass flow will be the same as the mass flow out. The conditions of the flow in will change. We'll have different temperatures, different pressures possibly, so the conditions will change, but the mass flow will remain constant in most cases. So that's the only definition difference between an open and a closed system. In a closed system, only heat and work can go across the boundary, but in an open system, we have heat and work and mass flow can go across the system boundary. But the analysis is slightly different when we do some calculations on these types of systems. So just to give you an example of a closed system, and I think that's part of the question, is to give an example of a closed system. Try and think of something else apart from what I've done. So if we look at this one, the first one is a closed cylinder. So it could have, should be a closed system, might have some air inside that system. And we're going to transfer energy either in or out. So if we transferred energy in, it would heat the air up, and that would increase the pressure in there, and that would push the piston down in that direction. So we'd have work in, and heat in, and we'd have work out. And that's in a closed system because through that process, there's no mass transfer across the system boundary. Yeah, so that's relatively straightforward. Not a very practical system, because all you can do is put heat in and then take heat out and it'll draw the piston back in. It does happen in some cycles where you have an air-driven cycle, which you can use in a closed system, gas turbine, for instance. However, another example, an open system, is a steam turbine is a typical example of an open system. So we have our symbol for a steam turbine, and the steam would come in, it would expand across the blades and then be exhaust off to the condenser. In that process, it would give up, the steam coming in would give up its energy, and that would be used to drive the turbine as work out. So we have mass flow in and we have mass flow out. We also have work coming out, and we also have heat transfer. Now, typically the heat transfer in a turbine, in a steam turbine, would be out of the system, so it would be negative rather than going across. That wouldn't be coming into the system. It's generally across because it's a high temperature, so it would be into a low temperature of the surroundings. So that would be out of the system typically in the turbine, in the steam turbine. However, if it's a compressor, we can use this same process for a compressor, but the in would be at the low pressure end and you'd compress down and the mass flow would be in the opposite direction. So a turbine, a compressor, gas turbine, steam turbine, they're all examples of an open thermodynamic system. Right, so that brings us on to task 2. And you're asked there, and I think it's a bit premature to ask this question, but you know, so we have to go down this route. So using a formula in each case, explain the application of the first law of thermodynamics to a closed system and to an open system. So first of all, what is the first law of thermodynamics? So the first law of thermodynamics states that energy can neither be created nor destroyed, only altered in form. And that's quite, you're probably aware of that term, that energy can't be created or destroyed. It can only change its form. So we're going to look at the equations that apply to a closed system and to an open system. Now, bear in mind, most of this development of these equations are in Unit 2. However, I've given you the equations here. For a closed system, Q being the heat transfer, W being the work transfer across the boundary, Q minus W is equal to the change in internal energy. So let's go back to a slide, to this one. So if we put heat in, then the temperature is going to go up and the internal energy is going to go up. So depending on how much heat we put in and how much work comes out, that's going to possibly change the internal energy of the system. So we need to know that the summation between the heat in minus the work out and the Q minus W, that's because of the sign convention, is equal to the change in internal energy. And I think that makes sense to you. If you had a kettle on a gas stove and you lit the stove, then the heat would be in, it would raise the temperature of the water, so the internal energy of the water in the kettle would increase. So delta U would be positive in that case. So closed simple is relatively simple in terms of the equation that applies. So that's the equation, no flow energy equation. Yeah, okay. So the next one is the open system. Again, we start off with our heat transfer and our work transfer across the system boundary. But this time we've got to be aware that the fluid, now there's a little drawing down on the bottom right here, is that we have a fluid flowing in. So we have fluid mass flow into the system in that direction. And we have a mass flow out of the system. Now, because due to the flow, that mass flow in and out has an energy term. So we have to take account of that in an open system. So we look at, first of all, what energy does that fluid have that comes in? Well, the energy flowing in will have an internal energy. So we have internal energy on the bottom, right at the bottom of the page there. So that has an internal energy, U. It also has what we call a pressure energy. Now, to get that fluid to flow into there, it has to have some pressure. Pressure times that cross-sectional area will give us the force, and the force times the distance the fluid moves is the work done, and the energy needed to get the fluid into the system. So we need to know what we call the pressure energy, the energy to get the fluid into the system. And what's done is that those two energies are combined. So we have internal energy and pressure volume energy. We combine those two together to form a new property called enthalpy. So the fluid has enthalpy, in this case it's H2, so the enthalpy out. But not only does it have enthalpy, it has kinetic energy, because it has a velocity, so it has kinetic energy due to its height above the datum point, which is mgz, so it's z2 looking at this place. So I'm looking at z2 here. It has potential energy at the outlet. It also has potential energy at the inlet. The other term that is contained in that equation is this kinetic energy. Now the kinetic energy is half m times the velocity squared. So it's got velocity, it's got a mass flow rate. So we know that there's a kinetic energy involved with the flow in and out. So we can't ignore that. So we have to take those into account as well. So if we look at the energy, that what happens, we have heat out, work in, we also have energy in, and we have energy out. Now the energy in is the enthalpy that it has, plus the kinetic energy, plus the potential energy. And same coming out is the enthalpy of the fluid leaving, plus the kinetic energy of the fluid leaving, plus the potential energy of the of leaving. And the difference between the two would actually be a gain in internal energy with the system, but that's not going to happen with a steady flow process. So that's the equation for a steady flow energy open system energy equation, steady flow energy equation for an open system. So that's, you need to use that equation to address part B. So in answering that question, you need to look at this equation, explain what the terms are, and that would be sufficient to answer that question. Okay, we're going to slightly move on now to task 3 and task 4. Now there's a bit more involved here. We've got to sort of define some of the thermodynamic terms to you. So we're going to start off by looking at the thermodynamic properties and the system state. So the state is really used to describe the condition of the system at a particular instant in time. And the state is usually defined by a set of properties, and those properties are things you can measure, such as pressure, temperature, volume, and mass. They're the ones that we're going to commonly use in thermodynamics. So let's go on to the next slide. We're then going to look at the laws of perfect gases. Now, these are all in the notes, so you're well worth sort of having a proper read of them so that you understand them. But this is a summary of the theory that's in the notes. So we're going to look at the laws of a perfect gas, and we're going to study the behavior of those substances so that the thermodynamic laws can be applied to real practical engineering problems and how the fluids behave. So some experiments were done by some scientists. Boyles Law, you may have heard of before, Charles's Law, and there's a constant volume law. And Boyles Law, we're going to apply these in a minute to a process. So Boyles Law is where you take a gas and you vary its pressure and its volume by keeping the temperature constant. When we say it's a constant temperature, we mean it's an isothermal process, isothermal. You know, like isobar is constant pressure, isothermal is constant temperature. So Boyles Law simply took a volume of gas, changed the pressure and the volume, keeping the temperature constant, and looked at what happened in that process. Charles's Law did something very similar, but this time he kept the pressure constant and varied the temperature and the volume of that control volume of gas, quantity of gas. And then we have the constant volume law, that's not assigned to anybody. And again, as you might imagine, the volume was kept constant and the pressure and the temperature were varied, and the results sort of analysed. So just to give you an idea of outcome of Charles's Law in particular, I don't know if anybody's ever seen this graph before. So we're looking at Charles's Law. So in Charles's Law, what you had is the temperature and the volume would change while keeping the pressure constant for two different gases, gas A and gas B. So you can see on the plot on the bottom there is we've got two gases, gas A, gas B, and we're going to vary the volume and the temperature. So that was done above room temperature in the solid plots. And what was noticed that if you were to extrapolate those graphs back to zero volume, it was found they actually touched the zero volume line at a temperature of -273. So if you can see, if you extrapolate those lines for gas A and gas B back to zero volume, then the temperature at which zero volume occurs is -273. And that became known as absolute zero and is known as 0 Kelvin. Yeah, so that's where that came from. It's based on Charles's law and the extrapolation of changing the volume and the temperature, keeping the pressure constant, and we were able to establish that the absolute zero is -273 Kelvin. So now we're going to develop the equation of state. Now I'm very conscious that I'm going through this at quite a rate of knots, and we're doing quite a lot of thermodynamics here. So you do need to sort of complement what we're doing by reading the notes. So we're going to develop the equation of state for a perfect gas. Now you see we've got 3 cylinders there, A, B, and C. They're the same cylinder, same gas, same mass in each one. And we're going to go through 2 processes. We're going to processes where we change the properties of the gas contained in that system. So we start off with cylinder 1, condition A. It's got pressure 1, volume. Notice the volume is in capital always, because it's not dependent on any other property, same as temperatures in capital, but pressure is in pascals or newtons per meter squared, so it's in lowercase. So we have P1, V1, and T1. We're going to undergo an isobaric process, constant pressure, that means. So we'll go through an isobaric process. We're going to go through a constant pressure process. So we're going to add heat into that gas that's in that cylinder. Now it's sealed at the edges, doesn't have big gaps. So we're going to add energy into there. So what's going to happen is, as the temperature increases, the volume will increase, but because this piston isn't constrained in any way, it's going to be allowed to move up and kind of air pressure on the outside, applying a steady force downwards. So that means it's able to expand. This gas is able to expand in volume, increase in temperature, but the pressure will remain constant because the force acting down is the same in A as it is in B. We refer to that as process A to B is Charles's law, and we can see from there that if we increase the volume, we increase the temperature. So that means the volume is directly proportional to the temperature. So that means we increase the pressure, the temperature, we increase the volume. They're directly proportional to each other. So that means the volume over V1 over T1 is equal to a constant, and that will equal V star over T2, the temperature T2 in here. You'll see while we'll call it T star, V star in a minute. We'll go on to the next slide. So we're just going to rearrange that a little bit. So V1 over T1 is actually equal to T2 over T1. Just rearranging that expression. Rearrange it again so we get V star in terms of V1, T2, and T1. Just rearrange it using an isobaric constant pressure process. Now, I'm very conscious that we're doing quite a lot here. So if you don't quite get it, understand what we're doing, ask me again and we'll go over it again. So don't be concerned if you don't get it the first time round. We will do this again if need be. Right, moving on to the next slide. So just bear that equation in mind at the bottom of this page here, where we've got V star in terms of V1, T2, and T1. Right, we're going to go on to the next slide. So now this time we're going to go from B to C. So process B to C, we're going to apply Boyles Law. So Boyles Law is constant temperature. So the temperature at point B, called T2, that would be the same as the temperature at point C. That's going to be T2 as well. So what we're going to do, we're going to probably do some work on that process. We're going to push this piston down. So what's going to happen as we push the piston down? the volume is going to reduce, and we call that V2. Also, the pressure is going to change, and there's a, see, I've put a capital P there, it should be lower P. The pressure is going to go up. So if we look at what's happening there, we've got an equation where P1 over V over T is equal to a constant, and that's equal to P2 V2 over T2. Now the T2s are the same, so they cancel out. And you'll see that P1 V star is equal to P2 V star. So we can rearrange that now. So we get V2 over V star is equal to P1 over P2. Again, I'm going to rearrange it, and that gives us V star in terms of P2 V2 over P1. However, we also know that V star is equal to V1 T2 over T1. So we can put that term equal to that term. So if we do that, so if we put this equation here, we know it's equal to, I'll just have to go back to remind myself. So it's V1 T2, V1 T2 over, let's make sure I get it right in case we, over T1. Do we? Over T1. Because we know that they are both equal to V star. So then we can rearrange that whole expression there. So just taking this expression, we can rearrange that to give this equation down here. So this is a very useful equation now. We've got P1 V1 over T1 is equal to P2 V2 over T2. Now that's going to be true for all processes. Yeah, no matter what the processes of going from A to B to C, whatever it is, P1 over V1 is always equal to T1 over is equal to P2 V2 over T2. So that is a very important equation in thermodynamics. So just bear that in mind because it's very useful. We won't use it in that form. We've found a way of making it easier to represent that equation. So we know that P times V over T is a constant. Right, we're happy with that. So it'd be useful to call this constant something and just calling it a constant is a bit odd, isn't it? So what we do, if we do this per unit mass per kilogram, if you like, then we can change the volume to its specific volume. So the specific volume is meters cubed per kilogram. So we can, if we change the volume to a specific volume, then we can call this constant something that we call capital R. Now, capital R stands for the characteristic gas constant. Now, that's different for different fluids. For air, I think it's 286 joules per kilogram K, but for different gases, it has a different characteristic. So just bear that in mind. Now, because we've actually changed that now to be a specific quantity in terms of kilograms, and if we make it for mass, if we want to put the mass term back in, we can then do the reverse of what we did initially. I know this is confusing. We can refer that back to its main volume because the specific volume is meters cubed per kilogram. So we can actually rewrite that equation as the pressure times the volume, which is capital, is equal to the mass times this characteristic gas constant times the temperature, just taking the temperature over onto the other side. Yeah, that's all we've done there. And that's known as the equation of state. So for any gas at any condition, providing you can measure the pressure and the volume, you can work out the mass, because R is a characteristic gas constant for a particular gas. It'll never change. That's what it is, unless you change the gas. So for instance, if you wanted to know the mass of air in a cylinder, in an air receiver, you can measure the pressure, you know the volume, R doesn't change, that's a constant, and you can measure the temperature. So you can work out the mass of air in the cylinder. You can work out the mass of air in the room that you're in at the moment. You get the volume, You've got the pressure, has to be in pascals. You've got the temperature, has to be in Kelvin, so they all have to be in Kelvin. So you can get the mass of air in the room. So, you know, typically it's about 1.2 kilograms per meter cubed. That's a typical mass. If you had a meter cubed of air, you could work out the mass. And you see, it will change with the temperature and with the pressure, as you know. So the equation of state is probably one of the most important equations we have in thermodynamics. Right, one of the questions asks how you can actually develop the relationship to find this characteristic gas constant R. And the relationship is, it's simply the specific heat at constant pressure minus the specific heat at constant volume. So that's the relationship to get our value, the characteristic gas constant. Now, the specific heat at constant pressure and the specific heat at constant volume, what we can do, just to sort of explain that to you, if we take a cylinder and we put a piston in there, and just leave it so it's free to move, and we've got some gas inside the cylinder. So we've got a gas inside that cylinder. All right, now if we add heat into there, so if we put Q into there, and we've got a pressure acting down, so we know that the pressure will be constant, because it could be air pressure acting down, or it could be a spring. So if we put energy into that, what's going to happen is our piston is going to move up, isn't it? So we'll draw our cylinder again. Rough, but there we go. So what will happen is, as that heat goes into there, the gas is going to expand and the piston moves up. Now, what the specific heat measures is the amount of energy that you put into that gas. So it's the amount of energy you put in to increase the temperature of the gas by 1 degree for each kilogram of gas. So the units are joules per kilogram K. So the specific heat at constant pressure is the joules, or the energy required to increase the temperature of 1 kilogram by 1 degree. Yeah, so it's the energy required to heat 1 kilogram by 1 degree. That's what we call the specific heat at constant pressure. Now, likewise, the specific heat at constant volume is that I'm not drawing that very well. This is my cylinder again. And we've got our piston in there. So this time what I'm going to do, I'm going to put a peg in there to stop it moving up. So I'm going to jam that piston. So we've got our gas in there now. And we're going to put some heat in there, Q. And what the specific heat at constant volume is, again, how much energy is needed to raise the contents of that by 1 degree for each kilogram. So the units would be the amount of energy, it's at constant volume because our piston is jammed. So it's the energy required to heat 1 kilogram by 1 degree. Yeah, and that's would be specific heat at constant volume, where this one here is a specific heat at constant pressure. So it's only a slight difference in determining the value of specific heats and constant pressure and constant volume. Just bear that in mind, and the difference between the two gives us our characteristic gas constant. I think that's one part of the question, if I remember right. But anyway, let's move on. Right, looking at some gas processes. I've been going on for a little bit. I hope you're all okay. Look at some gas processes. So a gas process means a compression or an expansion of a gas. What we need to do, we need to simplify what we had before. We had earlier, we had P1 V1 over T1 is equal to a constant. And we can simplify that in terms of pressure and volume. but we need to introduce something called the index of compression. So rather than writing P1 V1 over T1 is equal to a constant, we can simply write pressure times the volume to some index of compression N is equal to a constant. Okay, so, and that's what we're going to do in these processes. So there are some classic, what we call polytropic processes that are classic polytropic processes. So the first one is an isobaric, and you need to be familiar with these names. Isobaric, it stands for itself, doesn't it? Constant pressure system, compression or expansion. We can have an isochoric, so that's constant volume. That's probably not something that you're familiar with. Isothermal, well, that stands, it sort of suggests, and it's isothermal, so it's constant temperature. And then there's another system, another type of compression or expansion called an adiabatic compression or expansion, where there's no heat transfer. So in this, Q would be equal to 0. In the others, Q isn't 0. It can be a combination of Q and W. Constant volume, there's no work done because the volume doesn't change. So we can write W is equal to 0, but there will be Q heat transfer. So they're classic cases of the polytropic process. And we write that as PV to the power N is equal to a constant, or we write it as P1 V1 to the N is equal to P2 V2 to the power N. So they're what we call the classic polytropic processes. Now, if it's not one of these processes, and we will do these as we go through the unit, then it's just referred to as a polytropic process. So it doesn't have, it's not a specific case. These are the specific cases that we generally look at. But if it's not, doesn't lie within one of these cases, specific cases, then it's just referred to as a polytropic process. But don't worry about that at this stage. Yeah, it's not that important at this stage. Very important though, adiabatic process. So if you have a petrol engine or a diesel engine and you have a compression stroke that compresses either the air in a diesel engine or the mixture in the petrol engine, then that process happens very quickly, and it's very, very close to being an adiabatic process where there's no heat transfer during that compression process. So it happens very quickly, and it's very specific to that type of process. So it's a process without heat transfer. So a compression process and an expansion, to that matter, in a petrol or diesel engine is considered almost to be an adiabatic process. Just something to bear in mind for future assignments. Right, so what do they look like on a pressure volume diagram? Now, pressure volume diagram, we have the system pressure. So we're going to increase the pressure, increase the volume or decrease the volume. So in this one, if we go from point 1 to point 2, it's an isobaric process, so it's constant pressure. So we go from the larger volume to the smaller volume in this case. So it's a compression from V1 to V2. If it was going the other way, it would be an expansion. And the thing to note about that is that the value of N is equal to 0. So you'd have P1 V1 is equal to P2 V2. But the value of N, the compression index, is 0. So that would be 0. Yeah. So anything to the power 0 is 1, isn't it? So P1 would be the same as P2. So you can work out the area under that graph, and we'll talk about that this last time. The area under that graph is the work done during that process, or the work out or the work in. It's the work done during the process. We look at the next process, which is an isochoric. So again, should we go from 1 to condition 2. So we're going to increase the pressure, but we're going to keep the volume constant. That means we have P1 P1 V1 is equal to P2 V2, and the index of compression in this case is infinity. Let's see if we can draw an infinity symbol. That's infinity. Yeah. So that means if you look at the work done, there is no work done because there's no change in volume. Now, it's always useful to look at these graphs. The area underneath the graph represents the work done. In fact, it is the work done. So that means no area under the graph means no work done. So work done is equal to 0 in that case for an isochoric process. I'll go on to the other classical process. Is an isothermal process, so it's constant temperature, and we know the value of N is equal to 1. So again, we go from, let's have it as an expansion. No, we'll do a compression still. So it's a compression from 1 to 2. And we're going to go in that direction. 1 to 2, that means P1 V1 is equal to P2 V2. And the value of N, the compression index, is 1 in this case. So it doesn't really mean anything, does it? It's just 1. So that means we're able to, if we know the pressure at the beginning, the volume at the beginning, we know the volume at the end, we can work out the final pressure if it's an isothermal process. Again, we can work out the area done by measuring the area under that graph. So the area under this graph, that area there, that's actually the work done. That's W. That's W. Now you can actually draw it graphically and work it out, or you can integrate it, and we'll do that again, but it's quite a complex integration to work out the area. That's all integration is, by the way, is just work out the area under a graph. It doesn't do anything more, there's nothing more magical about it, it's just the area under the graph. So we can find the work done. So the last classical process is the adiabatic process. So again, we keep it the same. We'll go from 1 to 2. And so it's a compression. That's our direction. Again, we have P V is 1 is equal to P2 V2. And the index of compression this time, N, is equal to gamma. Yeah, and gamma for air is 1.4. So for an adiabatic process only, you don't put N, you put gamma in there. Right? And one of the questions is saying, how do you determine the value of gamma? Well, gamma is simply the ratio of the fluid specific heat. So it's Cp over Cv is equal to gamma. Yeah. So you can always work out what gamma is, and that's the index of compression, only for an adiabatic process. For all of the processes, they use the value of N. These are the classic values: 0 for constant pressure, 1 for constant temperature, and it's infinity for a constant volume process, and 1.4 for an adiabatic. And it's N, whatever it is for any other process. But we'll look at the classic cases. So that brings us on to task 4. We've answered task 3 sort of in between. So I'll go to task 3. I've changed the slides around here somehow. But let's look at task 3, how we've answered those. The difference between a perfect gas and an ideal gas, I'd want you to research that yourselves. Yeah, I'm not going to say what it is. I want you to do some research and define what the difference is between a perfect gas and an ideal gas. And it has, just as a hint, it has something to do with the specific heats and whether they change or not with the temperature. Second part B of task 3, was how the specific heats can be used to calculate gamma. We've just done that, and Cp over Cv. And then how the specific heats can be used to calculate the value of R. We've also just done that as well. Okay, so I'm not going to spend any more time on task 3. And then task 4 was, you're given a polytropic process, so you don't know if it's isobaric, isothermal, or anything else. You're just told it's a polytropic process. So you've got to determine the index of compression for this process. So you've got to start off with P1 V1 to the n is equal to P2 V2 over to the n. You've got the initial pressures, final pressure, initial volume, final volume, and the initial volume. Don't get them mixed up. So you have to put the values in. So first of all, you might want to rearrange that. So you have P1 over P2 is equal to V2 to the n over V1 to the n. Yeah, so tidying that up a little bit. P1 over P2 is V2 over V1. Because they're both to the power n, it's to the power n. Now to solve that in terms of getting the value of n, all you have to do is take logs of both sides. So we take a log of P1 over P2 is equal to n log of V2 over V1. And that's it. And from that, you can determine the value of n. So it could be as high as 2, 3, depends on the value. So don't worry about that. But there's an example in the workbook that you can follow. So similar goes for part B, the closed system again, isobaric, constant pressure. So the line is going to be horizontal. So this one's going to look like this as on a pressure volume diagram, PV, and it goes isobaric heating. So the volume's going to increase. So it's going to go from 0.1 to 0.2, and you're going to work out the value of n and use the same process. You know it's a constant pressure. You know the value of n. You've got to show that it's 0. Yeah, prove that it's 0. So we'll leave that one with you. So I know time's getting on. So we'll go to the last task, and I don't want to spend a lot of time on this because we're going to do it. It's just for you to explain what the usefulness of a pressure volume diagram is. So we look at, I've just said before, the area underneath the graph represents the work done. So if we look at this one, first of all, I'll do it in different colored pens so we can actually see it. If we look at the compression part of the process from 0.1 to 0.2, what the usefulness is, if the area under that is the work done in the compression. So we can just shade that off to make it clear. So that's work in. Yep. Now, to find that work done, we need to integrate that function depending on what the process is. So we simply integrate between V1 and V2 for whatever the relationship is between the pressure and the volume. We don't know anything about the process at the moment. So all you've got to do in this question is really to explain that the area under the curve represents the work being done during that process. So that's okay now for the compression. So now we'll look at the expansion. Go back to a red. So the expansion process, then I'll put it in as dots, is the total area underneath that expansion line. So I'll put lots of dots in just to take a bit of time, isn't it? So the work done during the expansion process from 3 back to 4 is again the complete area underneath that plot from 0.3 to 0.4. I'll just put a few more dots in there to illustrate that. There's no empty spaces. So the net work out is going to be, so this red is work out, that area. So the network, that means what's the useful work you're going to get out of that system is simply the work out minus the work in. And that's why you can't get very high efficiencies of any sort of reciprocating engine, because some of the work that you actually deliver in the power stroke, you have to use some of that energy in the compression stroke. So you're never going to get 100% efficiency out, because you've always got to use some work to drive the piston back up on the compression stroke. So the net work is just simply the work out in the expansion minus the work in during the compression stroke. And that's what we're expecting in task 5. So we don't want to go any deeper than that. Don't want to start thinking about the integration of these functions. They are different for depending on what the process is, and we will do that in the next couple of sessions. Okay, so that brings us to the end of this session. So just to go over what we've done before. When you submit your assignments, don't forget to include the contents page, as usual. Identify each task either by the letter or the number, so we know which question you're answering. Type up all written text. Now, equations can be handwritten and scanned either using lens or whatever you want to use. Don't take a picture, photograph, and just drop it in. That looks very unprofessional. So please scan them in and put them into your work. If you're going to use images to help explain your answers or to support your answers, you need to refer to those images in the text. So, for example, I'll put there, if you put an example in figure 2, nice drawing, put in the text, this can be clearly seen in figure 2 below, so that you link the text and the images. Otherwise, it has no purpose of being there. And don't forget to include accurate citation. That means where the reference that you've used in the particular part of the work, and have a very precise reference listing so that you're not accused of plagiarism in any sort of way. Okay, so that brings us to the end of the session. So if there's any questions, let me know. I'll just move on to my contact details if you need to get in touch. So please don't hesitate. We've done an awful lot of work today. So if you don't quite get it, you don't quite grasp what we've done, please let me know and we'll talk about it. We'll go over it. I'll ring you back. Send me your number and availability, and I'll ring you back. Not on a Wednesday, by the way, because I'm not here. But you know, please use the staff are here to help you and to make sure that